let us continue where we left off last time. Remember, we are kind of cataloging all the different contributions to the path loss. And we went to the major ones, like rain, and we calculated all sorts of things when it comes to the rain attenuation. And we are now going through the other ones that are contributing to the losses, but are not as prominent as rain. Remember, rain is the most dominant effect on a path loss, besides the free space path loss. There is a recommendation from ITU that I've placed on the website. This is a recommendation 618 that has pretty much all the material that is in a textbook and that I'm going to be covering. Just a little bit of explanation here. All of the recommendations that are pertaining to radio propagation or just in radio domain, they're ITU-R, and then all the satellite stuff starts with P, and then 618 is the number of the recommendation, and then -9 stands for the 2009. And then here you have all the revisions that this document went through. You know, they're regularly revised based on the new knowledge that we acquire in a given area. This one has all sorts of data, or all sorts of procedures that are pertinent to calculating the losses. And then it's very detailed. It's actually a better document than your textbook, right? Your textbook, maybe, depending what you're really looking for. The textbook starts just to give you an overview and explain. And this one is to the great detail about any of these things that we consider. Like, for example, here you have, propagation, attenuation due to atmospheric gases. We talked about attenuation due to oxygen and water attenuation. Then, prediction of attenuation statistics for an average year, seasonal variations, and so on and so forth. What we're going to be talking today is more towards the end. So I'll be, going through some of these. But, just like I always say, even the best instructor is worse than a worse book, right? So this is an excellent book. So you have everything that I'm trying to kind of say already in this document to the very accurately specified. I'll go back to this document when I talk about polarization losses, but let's just go to the regular textbook material. So these are the additional components to the path loss that I'm going to cover. Two losses which are called scintillation. Scintillation is what we refer to as fast scales. It's analogous to what we refer to as small scale fading in a terrestrial propagation. Now here you don't have a multipath, or so you think you don't have a multipath, but we're going to see how the multipath is created here as well. And there are two ways, how this can be created, and the result is very similar to the result that we have in the terrestrial case. Now there's something called Faraday's rotation. This is due to the magnetic field of the Earth. There are other reasons why we get the depolarization. And then the last thing I'm going to cover briefly is what are the things that we use to counter some of these losses. And it's very similar to some of the things that we do in terrestrial world, like diversity and coding and all that stuff. So there are two sets of things. One is going to be called scintillation, and the other one is going to be polarization losses. And I'm trying to explain the reasons behind them and what are the net effects that result from them. Tropospheric scintillation. Now, we are sending electromagnetic waves, and you know that the speed of the electromagnetic waves is determined through the properties of the medium that it goes through. Now, our atmosphere is not a homogeneous medium. It has variations that cause its refractive index to change, 1 over square root of epsilon nu. That changes from one location to the other location to the atmosphere. What that does is, if you send a wavefront towards the ground station, then it will kind of travel as a planar wave and then enter into atmosphere. And because of the different density of the atmosphere and temperature and all of these variations in the atmosphere, this would cause multiple waves to kind of bend. So you're going to get your direct line of sight that travels straight, but even the ones that are kind of in a close vicinity would sometimes bend and come towards the antenna. Now, what happens as a result of that, they don't come through because the antenna beam is very, very narrow. They don't necessarily come through the main beam. They may come through the side lobes, or they may come actually on the side of the beam. So we say that these waves are modulated with the beam. What that means is the one that is you're pointing that comes straight to the main has the highest gain. The ones that are coming a little bit on the side have slightly lower gain. Now, if you think about it, this is, and then these guys that are kind of bending travel different distance. Since their wavelength is very small, even the small variations in the distance that they travel result in a significant shift in phase. And when you have waveforms that are approximately the same magnitude, but shifted in phase, what do you get? Constructive and destructive interference. And here, nothing is moving. Let's say this is a geostationary satellite, but the atmosphere itself is moving, so that interference changes over time. And the result of that is fading. And here it's a temporal phenomenon, right? So if you look at, you have your signal that is, has certain average, and then it bounces on about the average as a result of all these multipath components that are reaching the antenna. Now, as I said, this has a very similar, if you were to look at the signal level, it has a very similar behavior to the fading. Not the relay fading, because you still have a dominant line of sight component, but some sort of Ricean fading with relatively large K, right? And it's not saying that in book, but most of you have been through the RF propagation, so I'm referencing that because you have already seen the math behind this. So this is how you might see the example of the scintillation losses. This is the loss in dB, and you can see the fading is on the order of a couple of dBs. Sometimes, these are what they depend on, operating frequency. That's just the nature. The smaller the wavelength, even the smaller differences in the path length cause significant changes in the phase. Depends on the climate. What I mean by that, the atmosphere itself. Whether you are satellite elevation angle, right? Whether you're going way up where the path of the atmosphere is much shorter, or you're going down close to the horizon where the path of the atmosphere and exposure of the path to the variations of the atmosphere is larger. Antenna beam, if the beam is wider, then you capture more of these multipath components. If it's narrower, it minimizes the effect. The way how we deal with this, we always you see the variations are on the order of a couple of dBs. So we can either incorporate some margin in our design and then mention that even when the signal is at its lowest, you still have a link, or you can deploy error control coding that when you go through some of these deep fades and lose some information, you can get it back to error control coding. Now, we use error control coding and interleaving to make sure that all of your errors are spread across the code, across the sequence, that they're not clustering as a result of these temporal fades. A lot of times, easiest way to model this variation is through something like this. It's called one-sided normal distribution, where this sigma is taken a role of the standard deviation. It tells you that what the distribution of these fades are, and typically sigma is 0.5 dB, and then you can kind of do calculations like this. You can, if you assume certain analytical model, you can determine what you need in terms of margins to guard against. And here there's this example. It's worked out in the notes. There's nothing particular about it. It's just that I wanted to kind of give you the order of magnitude. It's about 1 to 2 dB margin that you need to put in your link design to take into account scintillation. Losses due to the tropospheric scintillation. Now, besides the atmosphere, there's another layer that the signal needs to go through that will also bend the propagation of the signal. We talked about I think at the very beginning, that above the atmosphere there is something called ionosphere. In the upper layers of the atmosphere there is something called ionosphere. Essentially, this is a result of the sun rays hitting the molecules of various gases. And what they do is they create, depending on the sun activity, they would create ions. Ions are charged particles, and now you have your electromagnetic wave going to the charged particles. Now, they're not uniformly distributed. The density is not uniform, and as a result of that, you have the bending of the wave. And even though the source is different, the end result is the same. You have multiple ways of reaching the antenna, and those signals that are coming to the antenna, they end up having different phases and approximately the same magnitudes. Therefore, there is yet another source of fading. All right, these guys depend very much on sun activity, and they're the mostly pronounced in sunrise, during sunrise and sunset, where the length of the sun beams to the atmosphere is the longest. Now, Faraday's rotation, right? What we mentioned earlier when I talked about frequency reuse in satellite is that we utilize polarization so to effectively double the number of channels that we can operate in a given frequency band. You would stagger the channels, but operate them one on the horizontal polarization and the other one on the vertical polarization. So if you have, what did we have as an example? We had C band with 500 megahertz, where we were able to put 25, 40 megahertz channels, right? Which is, if you calculate 25 times 40, gives you 1 gigahertz. But because you are using the polarization, you're actually able to double the number of channels. Ideally, if you send signals on, let's say, vertically polarized signals, and you receive them horizontally, the crosstalk ideally is 0. Therefore, you can have, they're orthogonal, therefore you can use the same frequency but different polarization to essentially double your frequency, double your number of channels. Now, that is fine as long as you maintain orthogonality between the polarization. As soon as your wave starts bending and losing its polarization purity, two things happen. First, you get loss on the receiver that you use for the reception. Why? Because now the receiver antenna that was designed to, let's say, receive vertically polarized waveform has a waveform that is slanted, right? So only portion of it that is in the vertical portion of it, the energy will be received. Whatever is horizontally polarized will actually not be received. So you have some link budget losses resulting from the loss of polarization. That's one effect. The second effect is because of the frequency reuse, now your portion that is horizontally polarized is going to interfere with adjacent channels, because there's an overlap between them. So you have two things that are happening when you lose the polarization. One is you have link budget losses, and the other one is you have cross-channel interference to the adjacent channel interference. Now, why would you lose polarization? Well, polarization is lost because the signal propagates not through vacuum, but rather it propagates through the magnetic field of the Earth. As you know, the Earth has, is a big electromagnet. It is rotating, and therefore, all the excess charges inside cause this magnetic field that is surrounding the Earth. There are kind of a little bit problems with that field. First, it is when the signal travels through that, under the field, it will start bending, and you might want to try to take that into account, but the field is changing itself, right? So it's the magnetic pole is not on a constant spot. So over years, it will change its location, and you would have to adjust your transmission adapter. The rotation angle depends on length of the path to ionosphere, concentration of the charges and operating frequency. And in chapter 4 of this document that I have provided, this is kind of explained in much more detail. The polarization losses are determined as a function of this angle, which is angle beta in this drawing here, that tells you how much the polarization is slanted relative to its ideal reception. And this works for both polarization, either vertical or horizontal. You just have to orient the axis from. This beta here is called Faraday's rotation angle.
I have a question. Is there a benefit of using circularly polarized light then? You have like one mode that's
Correct.
Right versus left. And look at
Yeah, there is a benefit because you know you're not subject to these losses, right?
Yeah. Assuming that it doesn't decay in amplitude, I guess.
Correct. Yeah. That you maintain the circular polarization, but what happens as a result of this, one would have to do the math properly, but what happens, you may end up with elliptically polarized waveform, and that kind of the greater reception as well. Now let me see what the next thing here is. So this kind of tells you what. So there are two sources, principal sources for depolarization. One is the magnetic field of the Earth, and that is there all the time, whether it rains or shines. But also, you know, you can get depolarized because of the propagation through rain. Raindrops are not spherical, and as they fall, they kind of they get squished one way or the other. And as a result, the horizontal component is going to be attenuated more than the vertical one, right? Because the droplet, you know, if you think about it, it's not a sphere. It becomes squished this way, so it's longer than taller, right? If you can see it that way. And as a result, you know, if you send a wafer that contains both polarizations, then the vertical is going to stay larger than the horizontal, and as a result, the waveform that was like this would now rotate towards the vertical, because vertical stays attenuated less. Now that's fine in this drawing because I'm assuming the droplet is falling straight vertically, but you know, the rain is usually accompanied with wind, and then what wind does, it kind of makes the raindrops even distorted more. You know, they're distorted by the resistance of the air as they fall to gravity, but if it blows this way, then they're also tilted and have irregular shape. And as a result of that, your rotation becomes somewhat random, but the result is that the waveform gets depolarized, and that same effect that we talked about just a second ago, where you get some link budget disadvantages on your link, and then you have the cross, the adjacent channel interference. Both of them happen. Both of these are, okay, I'll talk about this one in just a second. It says here 618-6, that was originally when I put these slides together, but this one that I have posted today is 618-9, and here is where they talk in the chapter 4 is where they talk about cross-polarization effects, how much of the signal attenuation do you get in rain due to the loss of the polarization. And what they provide here is a similar procedure to the one that we did, I think, the last time when it came to the calculation of the phase margin. So you know, there are several steps, I think altogether 8 steps, and there's really no big wisdom in going through all of them in great detail. They're kind of scripted very much the same as we did for the other one. The algorithm is valid for 8 to 35 gigahertz. Below 8, the impact of the rain on the polarization is below 8. There's another document. What is it? The procedure. Oh, okay. So there's the procedure for scaling to frequencies down to 4 gigahertz is given a little bit later in this same document. So what I would like you to do is take this document, read it, and I have an Excel spreadsheet that I put together for this, but I didn't post it, right? Because I'm not sure if the ones that I posted you actually go to. So what my challenge to you is, this one is much simpler than the other ones. So what I would like you to do is to go and implement this, following the examples I did with the other Excel spreadsheets. Put this into Excel spreadsheet and let me know if you run into any troubles. We can compare the ones. But it's relatively straightforward. And then, the procedure is very similar to the other one. You calculate for a given reliability, and then you translate to the other reliabilities based on the equations that I've given. Now, these are there is another reason why you're going to have polarization, I guess, challenges here, is there is a natural, but these you can deal with, right? Let me explain what is it that we're showing here. If you're talking to a geostationary satellite, then depending on where you are on a globe, you're going to see what we call geostationary arc. Geostationary, now, what does that mean? If I look at towards south, then where is south? This way, right? Then you're going to see your satellites that your geostationary arc to be like this. Now, if you place the satellite there, then the one that is right on the same longitude as you are, they would have to transmit it just completely vertical relative to you. Now, for all the others, if they're positioning to transmit vertically towards the globe, because you're now not on the same longitude, you're going to be seeing these signals a little bit offset, a little bit tilted. And that's something that you can calculate. The tilt angle is given as this expression here. LE is the latitude of your Earth station, LS and LE are the longitudes of the subsatellite point and the Earth station. And this tells you how much the angle T is tau relative to the vertical. And what you need to do is, if you are receiving from the direction, you have to tilt your reception to understand that now the wave is not coming locally vertical, but it's coming slanted based on the position of the satellite on the geostationary arc. Any questions here, or go ahead?
Is it for designing the system?
Say again?
Is it for designing the system, and
To point the antenna at the Earth station, right? You have to actually you have to point it not only in the direction of the satellite, but also you have to tilt it so that you receive the proper polarization, so that you don't have polarization losses. Because even though they transmit, let's say you have it's not easy to see if I can draw. This is your globe, right? Let's say this is your geostationary arc. This satellite here is on, and let's say your Earth station is here. So this satellite and this Earth station are on the same longitude, right? If it transmits like this, right, it will be received like that here, right? So it will be vertical. But if you are on some of the other guys, then it's coming from not straight, above you or stay on the same longitude, but it's coming from over there. And if it's coming from over there, then it's oriented this way, right? So as you move your dish, you have to actually give it a little bit of a tilt to receive, vertically as it's being transferred. This is what I kind of tend to draw here. And this is how much this angle is based on your the difference between your sub-satellite point and longitude of the sub-satellite point and the Earth station, and then how far from the equator we are.
Hi. So you will talk about is it mechanical tilt or electrical tilt?
What is the difference? I mean, I know what the difference is, but you just have to make sure that you're receiving properly, that you have antenna properly oriented, right? If you do that through the mechanical, it's not so much tilt, it's a rotation, right? It's not tilt will be up and down. This is rotation, right? So that you align your polarization of the reception to the polarization of the incoming wave, right? And you can do that mechanically, or you can do that electrically. Depends on the antenna system. Okay. So we kind of briefly went through two mechanisms here that are in addition to. Let me kind of summarize what we covered so far. We talked about attenuation due to the wave propagation through atmosphere. And those are your gaseous absorption, right? We saw that there are two dominant absorption gases that are in the atmosphere. One is the oxygen and one is the water vapor. So that's the first one. That one is relatively small, but it's present in the clean air, and it is, I guess, depending on the length of the part, but it can be up to 1 dB, fraction of the dB. Then you have big attenuation that comes from the rain, and that one is frequency dependent and polarization dependent. And when it happens, it's relatively large, but fortunately, very hard rain happens quite infrequently. So we deal with it through the fade margin. And then we have components of like fast fading components that are due to scintillations, and then we have components that are due to depolarization of the wave. Now, how do we deal with all of these? Well, there are some of the methods that we have here, are listed here. Now, this is in addition to the fade margin, right? Fade margin is the design margin that we calculated last time. We mostly, when it comes to rain, we mostly deal with either fade margin or something called adaptive insulation. But these are other methods that we have at our disposal that are used or not used depending on the system and what the goal of the system is. The adaptive power control is a method where you adjust the power of the transmitter based on the power of the received signal. If the signal is subject to fading, and let's say that there is additional loss, then through outside signaling, the transmitter is directed to increase its power. And as a result of that, it compensates for losses. Now, there are a couple of things that are required here. You have to have something that's called closed loop, which means that the transmitter needs to have a signaling back from the receiver that informs the transmitter on what the power level is of the signal, or what is the signal-to-noise ratio, some sort of signal-to-noise ratio that you report. So I guess there needs to be measurement, and those measurements need to be reported back to the transmitter, and the transmitter needs to adjust its power. This is very, I guess, common in systems that implement some sort of some sort of multiple access, where you have multiple transmitters sharing the same transponder, because you will see a little bit later when we talk about multiple access, you try for the transponder to operate efficiently across all of these various signals, they need to arrive at approximately the same power. Otherwise, you may have, you may need to amplify signals that are vastly different in power levels, and that creates the interference between them. So that's one way of dealing with fading. Then, just like in terrestrial networks that are subject to fast fading, we can use the diversity. Problem here is that when you try to use diversity here, it is not on a small scale, right? It would be where you try to separate your receive antennas quite a bit, so that, let's say, you can even compensate for some rain losses, right? Because the rain is also local, and if your separation between the receive stations, for example, on the ground is big enough, you may actually be always able to avoid really, really heavy rain, right? Because even in the climate, when we say, remember, there are two kinds of rains, and really heavy ones are localized spatially. So by having multiple receptions, multiple points of the reception, you may be able to avoid really, really heavy rain. The probability of simultaneous fades is reduced with the separation between earth stations. So the larger the separation between them, the chances for reducing your chances of reducing the fade grows. So signal onboard processing. Okay, so this kind of goes back to our adaptive modulation encoding. In some modern systems, the satellite is not just a bent pipe, it acts as a repeater. And what that means is the signal is carried all the way from the RF to the baseband, where it's decoded and then possibly switched to a different beams. So it's like a switch in the sky. What happens there is the signals coming from the multiple locations can be examined in terms of their power, rate, coding, and as a result of the different fades on the link, the ground station or the transmitter in general can be directed to implement different modulation and coding scheme. In the digital communication, we learned that if you fix the power, then you can actually get different. You can trade your rate and reliability, right? So if you can get more reliable link by switching to the heavier coding or to modulation types that are having a smaller constellations, right, becoming more robust. This is, I think, illustrated here. This is, there's a standard out there that's called DVB-S2. That's a digital video broadcasting standard with 1 and 2. And this is extensively used for broadcasting in satellite television. And what you have here is kind of that idea illustrated. On the x-axis, you have the signal-to-noise ratio in dB. And on the y-axis, you have spectral efficiency. Remember, spectral efficiency is the principal measure of how good is your communication system. It is expressed in bits per second per hertz. It tells you how much of the throughput is the system providing for every hertz of the bandwidth that is given to the communication channel. This is here drawn for a 36 megahertz transponder, and it tells you, for example, that as your signal-to-noise ratio increases, then your ability to get higher and higher data rates becomes larger as well. Because as you keep on moving to the higher signal-to-noise ratio, the two things happen. First, you are changing your modulation scheme, And you can see here we have 5 different modulation schemes from BPSK, QPSK, 8PSK. This is 16 quant, and I believe this is a 32 quant. And so this is where you switch different modulation schemes, and then in between different modulation schemes, you have different coding schemes. So the coding scheme tells you the ratio of your overall bits relative to the information bits. So when we say the coding scheme is 1/2, that means for every information bits, the rate on a channel is double, right? So there's, for every bit that we send that contains information, we send another one to protect the information of the first one. So here's how this standard is given, and there's 1 to 7, quite a few different modulation and coding schemes that can be adjusted as a function of your SNR. And the idea here is that through the constant adaptation, you're actually always operating in the highest efficiency that is supported by a given channel. Because remember, the throughput that you can put through channel is always limited by your channel's capacity for. So here, examples here, if at this point, your signal to noise ratio is 4 dB, and you're getting only 50 megabits per second in a 36 megahertz channel, which amounts to the spectral efficiency about 1.5 bits per hertz. Right? But then, if you start increasing your power and your signal to noise ratio increases, then you at the signal to noise ratio of 9.5 dB, you switch to the 8 PSK, and you're able to provide 80 megabits per second in 36 megahertz of spectrum. So that tells you how much more efficient the channel is. Now, these are, as I said, adaptive, and if you have a system that supports this particular standard, depending on what your link budget provides, it can be adjusted to provide different data rates. So, and then the beautiful thing about all of these is that we are starting to see more and more standards in the satellite communication. It is not as standardized as terrestrial systems, like in particular cellular systems, because it used to be, or it still is, mostly common practice that you get the entire system from one vendor, right? You would get the entire, all the way from satellite to the communication equipment and all the supporting systems from Boeing or from Hughes or from big satellite manufacturer, right? So the need for standardization beyond just the channelization was not as big as it is in terrestrial systems, where you get phone from one vendor and base station from the other one, and the switching equipment from the third one, and so on. But more and more we're getting to the point where more and more satellite, particularly air interfaces, are being standardized, and DVB-S is one of such standards. So let me just do a simple example that illustrates some of these things. I want to refresh your knowledge of the normal distribution and how you calculate the normal distribution for two components. It says, consider the case when scintillation losses may be modeled as a random variable with a given PDF. F of L equals to 2 over square root of 2 pi sigma to the minus 2, minus L squared over 2 sigma squared L negative 0, 0 otherwise. Where sigma is equal to 0.5. Estimate the margin to guarantee link reliability of 99% with respect to scintillation losses. So here's what is happening. If you look at this, L is the loss in dB. L loss in dB. So here's what is happening. This is loss in dB, and this is how probability density function looks like. Below 0, it's just 0. So what we're saying is, I want to guarantee the reliability of the link, which is better than 99% with respect to these losses. So what is it that I need to find? I need to find what is the threshold here, let's call it L99, that is going to be exceeded in less than 1% of the time, right? And if I over-dimension my link so that, without these losses, the margin is this big, then I guarantee that 99% of the time, even when the scintillation losses happen, the link is still going to be operating above the receiver sensitivity. So how do we determine this? Well, what needs to happen is that it's integral from 0, or I have it here, from L99 to plus infinity of 2 times 1 over square root of 2 pi times 0.5 e to the minus L squared over 2 times 0.5 squared. The L has to be smaller than 0.0. This is the statement. The area under the curve here have to be smaller than 1%, because this area under the curve tells me the probability that the losses are going to exceed this margin that I'm using here. Now, this guy here is 2 times the Q function. I wrote it here in my notes as upper tail of the normal distribution with mu equal to 0, sigma squared is equal to 0 squared, and L99, and that has to be equal to 0.01. So if you go to the table, you get that this is 0.65. L is 0.65 dB. Now, L99 is 0.65 dB. Now, I a little bit cheated here in my notes because I have a calculator that does this for me. In case you don't have that calculator, you have to use the Q function. So let me say this is 1. Let me show you how you transform this by using the Q function. We're going to have to introduce the substitution. T is going to be equal to L over sigma, right? L over 0.5. L minus mu, which is L minus 0 over sigma. So what happens, you end up with the integral, now 2 times. This becomes 1 over square root of 2 pi e to the minus t squared over 2 dt plus infinity when L is equal to L99, then t is equal to L99 over 0.5. So L99 over 0.5 is equal to 0.01. So from here, you can calculate, let me call this y, right? You can go to the table and essentially do this 0.005 and calculate what this value y is. And if you do that, you end up with y. So from your table, y is equal to 2.58. Right? So you have to be 2.58 standard deviations away to get this 0.99. And then once you have y, then you can calculate L99 is equal to y times sigma, which in our case becomes 2.58 times 0.5, which gives you the same number, 0.65. But the idea is very similar, and in this case, I'm just assuming this particular distribution. Other distributions are possible. Sometimes this is modeled by using exponential distribution, which is a little bit more heavy-tailed than this one, depending on what the particular model demands. But the process is the same. Once you have the model for the losses, then you can put your reliability threshold, and that will give you the actual threshold for the losses in dB that would guarantee that the losses are below the threshold for a given percentage of time.
Now the 0.5, the sigma, that's in dBs, right?
Yeah, everything is in dB. Let me work another example here just to show you the calculations of the tilt angle. So this is the example 2. Estimate the tilt of the signal received and then estimate the tilt of the signal. The following data are known. The latitude of the Earth station is 28 degrees north, and longitude of the Earth station is 80.5 west, and the satellite is 73 north. Now, where is it that we're this 28 north, and this is if you look at this is here. So this is somewhere here. This is the Earth station that is 0. This is Earth station that is here in Mountain, Florida. And then if you look at this as being your geostationary arm, then this would be this guy that's above the Atlantic Ocean. That's a satellite, right? So if you stand where we are right now and look at towards south, then this guy would be in this direction, right? And then the tilt would be this way. This angle would be tilted.
So sigma is in dB, but how did we use that in the linear equation?
Well,
Then L99 came, we are multiplying the
just-
dB with the linear.
correct. This is just a random variable, right? We it's always like that. Remember the y it's in dB, right? Why are these losses in dB? Because all the losses are multiplicative, right? And we treat them as addition to the path loss, right? So the way how you would say, remember our overall path loss is going to be free space path loss plus, let's call them scintillation losses, right? Now, when we talk about losses, all of them are multiplicand. Like you attenuate something so many times. But when you transition into the logarithmic domain, then they all become additive, right? And then if you look at this random variable as an additive random variable, then you can model it to something like this, right?
And then the L99, you
That,
got Y and you got 0.65 dB.
oh, but don't get hung up on multiplying dBs, right? Now you have this random variable. Remember that example of how the scintillation looked like, right? It's like this, right? So you have your signal without fading. This would be your signal EIRP minus free space path loss, and then you have these additional losses that are in dB, right? And the distribution of these losses follows this this curve like this, right? So the most losses are this is the loss in dB, and this is now PDF of that loss, right? And you can see there's less frequently are these. So we're looking for this threshold here, L99. Now once you pose the problem mathematically, then you detach from the physics, right? And you just do the math, right? And you say what is this threshold, so that this is satisfied. It's not unlike, remember when we did log normal model in RF propagation, then we had this guy here. It was also
Shadowing.
yeah, shadowing, right? It was a zero mean random variable with 8 dB standard deviation, right? And then when you calculate the margin, you do the z-score times the x sigma, right? Times the sigma, right? Over there, we also multiply the dB. So going back to this problem now, this is the location of the Earth station, and this is the location of the satellite. This is the sub-satellite point here. So sub-satellite point is to the east of this station. So if we look south from our Earth station, then the signal is coming from east, and therefore it will be tilted towards east. And the amount of tilt is calculated as tau is equal to 90 degrees minus arctangent of tangent of the Earth station latitude divided by sine of Ls minus L. And when you plug in the values, this is 90 degrees, or I should say, well, when you plug in the values, this becomes 90 degrees minus arctangent of tangent of 28 degrees divided by tangent, or it's not tangent, sine of 80.5 minus 7, everything is. And this gives me 13.8 degrees of tilt. Now, which direction is this tilt? This direction, right? This is my expected reception. The vertical at this point, it's tilted in this direction by 13.8 degrees. All right, so if I would receive it, I have to receive it this way, because it's coming from the left, it's coming from the east. Okay? Any questions?
Yeah, can you explain again how you...
Again, this, well, think about you just have to a little bit. Let me see if I can if I can draw it. I mean, it's not easy to draw, right? If you look at this arc, right? Let's just start doing some mind experiments, right? Where is this arc? It's right above the equator, right? So if I were to stand at the equator, where would that arc be? It would be above, right? And it would go east-west, right? So it would if this is north, it would go like this. Now, if I start moving up north, what happens to the arc?
So behind you.
It's behind. Let's say I'm now looking at south, right? Even though this is north, right? But it's easy for me to, or you want me to turn and look south, right? Then we look south. So what happens to this arc? It starts moving this way, right?
Yeah.
And as I start climbing in the latitude, what also happens to the arc? It starts falling down, right? If I go and I get to somewhere around 80 degrees, where is my arc? It's right aligned with the horizon, right? That's where I lose the coverage for the area close to the poles. So in general, when I look towards south, my arc is going to be like this, right? Right? That's how the arc, the geostationary arc, is going to look like. Now, if this satellite is to service, let's say, certain area of the globe that includes its satellite point, then it cannot adjust its transmission to every single point. It just has one transmitter, right? And then you are receiving it at different locations, right? So if I assume here that I'm transmitting vertically for a given longitude, right? Then if I move east and west, there will be some tilt of that signal, right? If I'm transmitting, if this is where the globe is, and I'm transmitting this way, then if I'm locating here, then I start seeing this as tilted relative to my reception, right? To my local vertical, right? And this is what happens. If you're on the same longitude, then you receive it this way. This is now my horizon. I should maybe kind of see it like this. Right? So here, if I'm on the same longitude, now this is viewing from the standpoint of the Earth station, on the same longitude as the satellite, then I see the waveform this way. But if the satellite is to the east, it tilts this way. If the satellite is to the west, the signal tilts this way. So then, you have to adjust your reception. And the amount how much you adjust is given by this expression. I don't know if there's a derivation of that in the book, but it's just one of those things you have to stare a little bit before you go.
Professor, in example 1, L99 works out to be 1.3.
Say again?
Why?
Why?
L99 works out to be twice, 2 times 0.65.
Oh, okay. So you're saying that this is not correct?
Yeah. It's 1.3.
So what is it? It's a 1.3.
Why should
Why was the question 1.3?
Let me just, I see what, but let me actually calculate. We have time, so just to make sure. Do I have a calculator? Do you see what he's saying? He's saying there's just this is not true, right?
Yeah.
Right, so let's see which one is true. So let me first verify the other guy up there. So if I put 0, 0.25, and 0.65, So this is,
Also,
because I forgot here, I forgot two. So this needs to be 0.005. And then when I calculate now, I mean, again, put 0, 0.25, and put 0.58. So the answer here is, this one is correct. It's 2.58, 1.2. Sorry about it. I forgot, I forgot this two. If you take the upper tail normal of 0 and 0.5 standard deviation, and you put 0.665 here, then you get 1%. But it has to be 1% divided. So this is correct. The first one. Any other questions? So okay, so on Thursday we're just going to be doing problems preparing for